Yeah, so then welcome back to High Performance Computing, Lecture 2 today, Parallel Programming with MPI. And basically this connects us to nice practical problems where you also will have your first assignment handed out next week. We can talk a little bit about this, and I will also introduce this a little bit now during the lecture. There will be also a practical lecture 2.1, where everything which I basically explained today will be also put more into practical terms. You have seen probably lecture 1.1 already, which was very practical, where I show how it's done. We do the same thing also with 2.1. So today we really have a more conceptual idea of MPI, but as you see from the outline, it's pretty much connected to really practical problems. But before we go into the material lecture 2, let's connect it nicely also, which we heard the last time. And we have basically learned that C and Fortran is still very valid today. In fact, I just had talked with a PhD student who is working in Fortran and CFD, and you know him, it's basically Reza, right? We talked about Grindavik and modeling there, some lava flow and so on. So it's a very in vogue topic. However, of course, this course is not about learning to program C perfectly, learning to program Fortran perfectly. That is not the goal of the course. Here we really try to get parallel computing taught. Right, so what you can do with these HPC machines. However, if you go to very much physical problems, we have some physics here, experts here, you will find again and again that HPC is really needed. We have seen the airplane, for instance, and the example of the groundwater modeling that in fact needs to take into account the basically land surface and the atmosphere connection and the atmosphere itself to really model the groundwater. So you would have C codes for all of those in the different levels of granularity. And basically to compute these elements over time to really understand the groundwater modeling, for instance, is something where you really need HPC for. And all of these softwares is written in C. Hence, last time we motivated a little bit, C is still on vogue. And we basically used it with a Hello World application, admittedly a very simple application, but we will come to more elaborate ones and when Reza takes over the second part. No matter if it's C in that regard, and we have also talked a little bit about the nest, so basically a brain simulation or sort of at least partial brain. We cannot really simulate the human brain yet, otherwise we would have other problems probably. So it's just parts of the human brain and the functionality. So, and these were more traditional simulation sciences, again, driven by, I would say, known laws of physics using numerical methods. What's also very new in the HPC world and more use is then the idea of using AI. We talked about this a little bit the last time. This is one example where we use it in remote sensing, but which application is not so relevant, we use AI. So deep learning, and you see quite the speed up, right? So the time it takes by using 1 GPU, 4 GPUs, 8 or 16 GPUs. So we break it down in basically the time to solve. And the term speed up is not really obvious to you. We see how that materializes when we have lecture 3. We talk about then some of these, let's say, terminologies which you really should know. Here now the takeaway message is that basically the code is existing, TensorFlow, PyTorch, deep learning packages, and they also are basically part of the HPC ecosystem now. So it's not only physical applications, but also AI applications. Particularly if you also remember nowadays in hyperparameter optimization. We learned as one takeaway message, however, when we tried this Hello World fun application, that there are some, let's say, ways how to do it wrong in HPC. And that's important to teach in HPC. What we don't want to use is the login node very much. If you remember, we used SSH, going onto the earlier login node. And we looked it up that it was a very weak sort of CPU. It's good for a couple of users, but not for really number crunching, not for compute intensive tasks. It's good for compiling on the login node. But as soon as we want to really compute solving something, physics, the solvers, we want to use the earlier compute nodes. Hence, just basically compiling, as we learned, the Hello World program and then executing like I did here, for instance, in the practical lecture 1.1, showed us we can Hello World, okay, give it out directly, but that's not how you use a HPC system, right? So the wrong way, if you do it and you, let's say, leave your nest running for 48 hours on the login node, which would be anyway questionable, the administrator will ring you or basically have your account blocked. Hence, there needs to be a right way, which we also teach the last time. In order to understand that's outside, okay. So in order to understand the right side of doing it, it's good to think about the broader picture, right? So think about that these HPC systems are shared with many, many different users, right? If you take about 3 exascale systems or the Joule system here, this could be 100 users at the same time. They all use the system at the same time. Hence, we need a manager of sort, a management system. We call that a resource management system that takes care of all these jobs. And what you see here is a little bit a kind of, sort of fake thing, but you would say parts of the machine could be used by an earth science application. Parts of the system can be used by a brain or neuroscience applications, and others use it for AI at the same time. So in a way, you have a graphical view of all the racks that we have seen before. In lecture 1, for instance, there's another earthquake simulation here, and actually some of the nodes are not in production because they're in maintenance. For instance, the rack needs to be changed and so on. Hence, what happens is you have a sort of schedule, and that motivates a little bit the name of the lecture last time, scheduling of users, right? So it's like the bakery we discussed. You take a number, and at some point in time in Biko, bakery, wherever, basically your number is called. It's a similar principle in the HPC machine. You have a batch queue, which we call that, and basically you submit your job using a batch scheduler, which you see a little bit here, and it shows also the right way. Oops, sorry about that. So then you basically see that we don't use a login node really for anything, just essentially for compiling and perform the S-batch operation. This talks about the scheduler to really then distribute this job on all the compute nodes. And this could be basically, of course, as we had the last time, just one node and one task per node. So a very simple job. In the end, we just use one core. But here is a job script also to your service, basically, to change this. And you could have different nodes, like 5 nodes, 6 nodes, whatever your application needs. And obviously, then also more tasks per node to execute. Hence, this is the right way because essentially, you now go away from the login node. You just have literally the S-batch operation. The compute-intensive parts are there. When your time has come in the schedule with your job, then you execute it. And what is the problem? You're not anymore in front of the screen, right? Hence, there needs to be something with the output. When you do it the wrong way, you basically get the output immediately, right? You have this hello world directly out. Now, how the work systems, the scheduler and the workload systems work is usually they dump the results into a specific output file. Now, this is a text file in our example showing just hello world, not really rocket science, but in, let's say, further elaborate application examples, you have something like HDF5, big, large arrays, multidimensional arrays, or even TensorFlow dumps of deep learning networks. So hence, something which is, so to speak, not anymore so interactive, right? You will basically submit your job, you can take your coffee, and at some point in time, you're started. We learned a little bit about algorithms that then improves the schedule. Basically, you could say first come, first served, obviously. But maybe sometimes if you have a very small job like we maybe can be backfilled. So if there's a hole in the schedule and we fit inside this hole, almost like Lego bricks, then we can be scheduled, although we maybe actually submit the job later than others. But as the schedule has just time for us, it will schedule us in, which is then another scheduling policy which is often performed. Hence, another way of using these systems than your laptop, right? Or like with a Eclipse IDE or so. That's important to realize. Then we motivated just a little bit also the extreme relevance, not only of training deep learning networks today, where HPC is beautiful, also here with a deep learning application you see here on the top right. Also for the online audience, I need to do the pointer here a little bit. So these are the hyperparameters which we then optimize with neural architecture search or things like RayTune. I think there's a question in class. Yep, 1 second. I will repeat. So there's a class question of how do you know how many nodes and how many number of tasks you need for a certain application? And this is a very good question, a valid question. And this relates a little bit to the application field. We will talk about how we, for instance, do a Cartesian grid, maybe let's say 4x4, a typical grid, and we want to simulate fish swimming in it. So hence it makes sense maybe to think about that each of the Cartesian block gets one core to solve the fishing of the swim. Then we maybe put 16, right, as number of tasks. Now the number of nodes is a bit dependent on the architecture as well. So we have a certain number of, let's say, tasks that we can do or cores that are available per node. So you need to know the architecture of the system. You have to use basically the documentation. If you go to Euro HPC JU, to the system Leonardo, Lumi, they will all give you the hardware specifications, how many CPUs per node or how many GPUs per node. And depending on this and your application needs, you would actually steer that. But it's also something which sometimes will grow. So you start small. It's something we do also in the next couple of lectures, where you start small in programming, but you would extend more and more, making it scalable. In other words, usually people don't start necessarily with using a 1 million cores, right? They would do smaller parts, let's say the Cartesian, very small with 4x4, and then extend to 10x10, 20x20, make it more detailed and more accurate over time. But good question. We will also come back to this again and again. Actually, today we will also extend the number of tasks to 4. So the first idea of programming parallel. Good, answer your question? Okay, cool. Then let's go ahead and dive in the material of today. And you see it's a bit out of sync. Normally, let's say we would have done and started with parallelization fundamentals. We did this based on student feedback so that we can hand out the assignment already next week, right? So that you get started early in the assignment so that this not all comes at the later parts. Hence, we injected here this kind of more practical topic MPI really into the sequence so that you can start early. And the topics of today will be, again, thinking about parallel computing, parallelization, how we use a message passing interface as a de facto standard really in distributed memory programming. Then there's an important term called portability that is important for you to understand, mostly because we have always very different HPC systems we are working with. And in order to basically use your application on this particular HPC system or in another, depends really on how portable are you with basically the MPI standard and in your application. So you can, in one way, take it from one HPC system to another. The point is you need to get computational time on all these different machines. Hence, you will not work in practice always on one dedicated HPC system, at least not over your career after 10 years. Chances are that you use around 15 to 20 HPC systems. They are all different in nature, but what they share is they offer MPI implementations. And with this, you're getting started, you get your applications portable. Hence, we talk a lot about this. Then understanding MPI is an important factor. It has point-to-point messages. We already understood from the last time it's about message exchanges, as the name suggests. But there are also MPI collectives, which are very smart to address suddenly not only one core, like a ping pong, right? Let's say that you want to program, but what about if you want to address directly 1,000 cores, right? So there may be something which is a collective operation to all the others. We will talk about this as well. And to really understand how you then have the kind of flow of the application in the MPI ranks and communicators, this will be something which is also a very practical part. And when you explore your own applications, we'll also see that this is something to understand really the behavior. So every basically rank is unique. Then in the second part, we will do some parallel programming basics. Hence, it will be very practical oriented. Although it's a conceptual lecture, we go step by step by step how to extend now our C program to a parallel program based on MPI. We set the foundation in practical lecture 1.1 with a C program, a valid C program, very tiny. And now we want to execute it 4 times at the same time in parallel on a HPC machine. So we will extend it, and I give you a stepwise walkthrough how to do it. I still will offer you lecture 2.1, which will be on Monday, where I do, the practical points when I log into the HPC machine, demonstrate it like I have done in 0.1 and 2.1, right? But it's already an important part because things are related to your first assignment with MPI, just reusing that and understanding the parallel application. Then ping pong is just as an illustration here. The same is true with the collective operations and so on. So we will do this in practical lecture 2.1 more, and I will demonstrate it there as well. Hence, when we're ready today, it's really parallel programming, as the name suggests. You will understand how it's differently from the hello world we had before. Then that there are different abstractions of parallel computing on various levels. Hence, we have collective operations with communicators, where you can address thousands of cores at the same time, or a whole Cartesian grid. Then basically, you will see we make a context always to scientific domains that will adopt this MPI standard for specific applications. So in a way, then you really, are having your baby steps to start with really programming your own applications in HPC. So let's see what we start with. And this is something maybe when you compare traditional serial programming, some of you have Java programmed before or so in serial terms. Yep. So some of you, this is really where you think about, right? You have arrays, you have variables, some in, basically in object-oriented programming would have then also different languages to think about. C++ as an extension to C. You have classes and so on. So we'd think about very different elements, which languages you want to use, and you have different implementations of compilers or interpreters in Java. So that's how you would do serial programming a little bit. Now in the message passing parallel programming, we think about other concepts, right? This still is in a way relevant. Of course, we'd have a certain language to program in, but this needs to be extended to a couple of things. One is, for instance, a concept. So do we do a single process, multiple data? Do we just do simple send receives to another processor? Do we have collective operations, again, addressing, let's say, maybe all processors that deal with this large Cartesian grid over time? I don't want to make a ping pong to everyone. I just say, maybe this is a new information. The wave height is like this at this point in time. And I address everyone. There are certain libraries today. We talk about MPI. You have heard shared memory as another one called OpenMP. And then, of course, there are different implementations of those. It's a standard MPI. But of course, there are different implementations that do some internal elements differently. So by looking in this in the practical application example, again, is glacier calving here. So you see that a little bit to understand what we mean by this is basically you would have a different physical, let's say, way how you have a glacier and how you basically then have a calving happening. So where parts of the glacier actually are then slowly deteriorate, so to speak, in the ocean. And this would be a physical different model. And this is another example that both of them are basically very computation expensive. This is still a toy application using 16 cores, maybe for the idea where it's basically carves out. And here you see the process. It actually goes now into liquid. And from this, the whole physical boundaries will change. We have a whole paper on it, basically, so you can read the details in there. But this is a typical application where you have some mesh generated, how the glacier looks, and then you have a different solver later on and use it then also with 560 cores instead of 16, because the process then in the water is much more elaborate. And this is just one example of one HPC application. The next one would be maybe modeling the polar bear running on top. But just to motivate you a little bit, what are these type of applications we use HPC for? And of course, parallel computing now comes into the game that over time, over this landscape of this glacier, right? This could be even Jökulsárlón, maybe, those would have been there. So we want to have something communicated. So when the glacier is calving, parts of it go into the ocean, we would have some location change of data, right? And these elements. So hence the processes that over time do something want to communicate something about the Cartesian grid and would to say, well, now the glacier at this time step has, broken into the ocean. Now the next time step, what happens with this? And so on, a very practical application. And the idea is really to do it in a cooperative way, as we already basically established in the beginning of the course. We review here. I just want to motivate two things. We have talked about this already in the let's say, look back to practical 1.1 part. But now if you had this kind of groundwater modeling, we said, okay, we want to now make a domain decomposition. We want to use maybe different cores in parallel. So firstly, we have to think about how we now have this domain of Earth and land cut down into different pieces, right? Here you see, for instance, an example on the top, at the bottom left, that here we break into 4 different blocks. So this is called domain decomposition. In lecture 3, we talk much more about it, but it's a very, let's say, homogeneous way of doing it. And the other element that I want to motivate is then this message exchanges, right? So the polar bear is running from tile A to B. So we have to communicate this is, location is going somewhere else. The glacier is carved and is somewhere in the ocean. It's flowing in this direction. So you have some physical variables usually. You have to basically give as messages to the other processors. Hence, the same is true with that what we also established at the beginning. When you think now the applications we have, and we will really have some more applications, coming to later lectures than in deep. But also here, when you have, for instance, a turbine modeled, what you do is you do a mesh, the kind of a grid that you see here. And we basically then would do a kind of mapping to different cores in this mesh, so that this aircraft is not anymore computed by 1 core, but by 500 cores, depending on the meshes, depending on our application problem. And that's how you try to solve it over time, like the animation nicely suggests, to compute certain aspects like stress in the turbine, right? This could be rate. Here on the right side, here the red parts, which then informs is the material correct, is the design correct, and so on. Just another application that you see why we need HPC really for these physics applications. However, physics is not the only driver. I told you also there's AI these days, machine learning. Not everything is deep learning. So you have here one code. We created a clustering code. One of my PhDs who finished a long time ago, but still the code is still the most highly scalable clustering algorithm that's out there, HPDB-scan. And what you can do is basically here in a, let's say, brain slice from human brains, identify different cortical layers based on their cell, let's say, amount, how they are in proximity to each other. So Euclidean distance in a way between the different elements. And this can be done nicely with HPC as well. You see here the number of cores and using, of course, MPI. That's why I bring this example. It's an MPI code. And linear scaling will be part of lecture 3, so you don't have to understand all of that. But of course, what we try to have is a code that basically scales with a number of cores. So the more domain you put, let's say, here you see a point cloud basically reconstructed from the inner city of Bremen. Here you see the whole Netherlands, basically reconstructed from a point cloud, from a laser scan, using clustering. So obviously these are different demands, and you need much more CPUs, much more cores to really have this done. And you have here sort of conceptual point where you see maybe not all the points are also very close to each other. Some of them are basically very isolated. So here we talk about domain imbalance, right? So here we have to do a smart solution of mapping then the different processors to these different problems. Hence, it's not that easy to chop down everything like pizza pieces. That's what I'm getting to. And we have lecture 3, which talks about this much more about domain decomposition. But here, just for you as a motivator, MPI is very relevant in almost all applications in HPC. Now, supporting it with modular supercomputing, you have seen this already a lot of time. We can use a cluster module very nicely for it. If you remember, often this is the high single thread performance CPUs that we're talking about here, and we want to use many of them in parallel. And to think in parallel, really, I think that's something what you really should get out of the first lecture part here. If you want to do a race car simulation, for instance, a race car over time, you have a couple of steps to think about it. You can also think about the heat in the room here, right? So we can compute this easily, but there needs to be some checks first. We have to do a good parallelization method. So do we want to chop up the room into equal parts? Or is for the heat maybe this part much more computation intensive because we have windows, right? Or there's a door, or there's a heat ventilation somewhere. So these are practical concerns. Maybe the Cartesian chop down way is not the best. Right, manually good MPI code is challenging. So the chances are there's already a solver, a library. Things like ANSYS is there, or OpenFoam, we will also have in the course more. There's already some libraries, right? But you would maybe do this initially on a couple of cores, will write this MPI code or use it, and then you will integrate it step by step with a technical, basically, problem in hand. You may use the wheels, then you would add, part of the chassis, and you would add the driver. So basically, what I'm saying is it's iteratively done. Usually, you don't plan the whole system perfectly and bring in parallel, because this programming is quite intensive in the brain for a manual, person to do. Hence, we do it, let's say, again and again in an iterative fashion to make it bigger, bolder, and more beautiful, as we would say. And why we have to do MPI for it is now the point to connect to it. We want to use several cores, but we learned in the lecture 1, we have a problem here that we basically cannot get to the other data, let's say, from the left wheel to the right wheel. That's in another processor, right? And we can't access a memory and don't know anything about the wheel. Hence, we have to do message exchanges to understand something, but the airflow that we want to compute in generally is basically affecting both, right? So some chances are that you basically need to interact a lot with these throughout basically the computational time. And there's often one element which is often, in physics at least, very relevant. This is time steps. Hence, we will talk in lecture 4 more about it, this time steps over time to simulate the physical phenomena. The same is actually true with AI, with epochs, right? There are certain of learning steps and epochs they will do, but still also a very typical way of doing it. The good news is MPI is something we don't have to do from scratch. It's basically an MPI implementation based on standard that we will just pick and can program our MPI application. And there are many different out there, Parastation MPI. We use OpenMPI, we will see also in the practicals. And again, a kind of idea why we now do this, maybe looking into one of these, right, from these red things that are introduced. You can see it a little bit like here how it works. You have your 23 in your own, process as a variable. That's a problem for process 2. It has no idea and cannot access this variable. It's in a different memory space. Hence, the process 2 needs to receive to get this. And in order to be ready to receive, basically when you throw someone a ball, right, you need the other player to be ready. Now, the handball analogy, you cannot just send and, then the guy will lose a ball. So we have a send and receive to implement that, the process 2 is ready to receive something and then can basically do the math on its own processors. Both will have the variable A. But once it's 23, once it's 24. Hence, I have to send it and then do something with it. It's just a very tiny application just to show you again, the memory spaces are separate and we require a send and receive. So more from the technical perspective talking, MPI is a standard with 200 functions and more, but actually was many applications use around 12. And they are not only send and receive. As I said, that is, of course, one of it. There's also this kind of collectives we will talk about. We talk about this with point-to-point versus, using different collectives. And there are different languages that support this now. There's MPI in Fortran and C. There's actually an MPI for Pi, an MPI for Python, and so on as well. And the different versions might be installed on all the different Euro HPC systems or here in Iceland. But basically, we can, with a module load system, quickly come and, basically get our version we want. Why we want to do this? And this is now an important part. If you go basically in a career in sciences or so where you need HPC, you will be faced with different HPC machines over time. Like you have now, basically almost our Jotun cluster is not there anymore. We put a Jotun partition on Elia, and the architecture and everything around it is different, new CPUs, new GPUs, etc. However, the old code that we had on the Jotun machine, because we use the MPI library standard, we can take and port to any machine that is implementing the MPI standard. Now, coming back to your question, which was very well observed, that's true partly. For the application, it may work, but still the job script for the scheduler might be to be adopted, right? Maybe we have a bigger domain Maybe we don't have, so many CPUs per node, just much more nodes. It depends, but it's in part which always goes together, the application and the job script. And often the job script needs to be more changed than the application itself. Because in a way we want, as a programming model, so to speak, that this MPI application is always scalable and portable. It has limits, obviously, especially if you think about, accelerators today. If you go from an accelerator machine using GPUs with CUDA to a system which has, let's say, AMD GPUs, and then suddenly no CUDA, that doesn't work anymore with portability. So there are certain, boundaries, but it doesn't affect MPI necessarily right now. One thing before we have the first part basically summarized and closed is also to think that although we're sending messages, it's not something that you would do for using a chat client, right? Or do something like Skype or whatever. So the idea is here not to use it over the internet because it has basically no security. It is a very, let's say, streamlined low-level protocol just to have the process interaction, right? So you should never use MPI really over the wire, basically connecting two HPC machines across basically the bigger internet. That's just an important part to see. So it's not really another network library that you would use in the later internet or another application. More conceptual aspects, the exchanging data with send and receive. A little bit we had this already with the memory space, right? We see here the two processors, compute nodes. Here we talk about point-to-point communication. Basically, I send this processor the new, but he has to be also ready to receive. But both have, different data in their memory space. Hence, also here, MPI point-to-point communication is taking place, send and receive. And then basically you can do something in your own memory space. It's basically similar like I had presented here. Now we're putting it a bit bolder to make a case later with it. Then now the other thing we didn't, and in contrast, we didn't talk about so far, was now the, let's say, collective operation. What happens if there's one processor that has a key data that is required for all the processors? Hence, there needs to be collective operations that take, let's say, our requirement of send, receive, send, receive 500 times in a loop, yeah, basically to a new concept on tree-based implementation and so on. That's not so relevant for us, but it's much more easier. I just say broadcast, a certain communicator, hence this term is loaded, we talk about this later, and automatically address very many processors. And this is then something depending on a so-called MPI communicator who is really listening to get these updates. Must not be all processors. We will talk about this very, very much in detail also in the second part of this today. Then you have scatter, another type. You have maybe an array that you want to distribute on all the different cores, another type of a collective operation, right? Again, you would basically chunk these arrays and put it into different processes for a computing, and then you collect the results maybe later. We call that one-to-many. Obviously, there's a counterpart to it. So if I collect then all the data that is basically coming maybe as a computing result over an hour of computing, I have the gather operation, which then from many cores come back to one core, right? So this is a kind of counter collective if you want. And you see also some source code, but we will do this also in the second part and also in practical lecture 2.1. I go more on the source code level. Just that you got the conceptual ideas, right? And there's one interesting one, which is reduce, because it always adds a certain operation to it, right? Reduce here can not only gather what you have done in all the different processes from the memory space, it can have a small operation to it to make it easier. Usually you want to have a summary or a sum up or a multiplication. So all these are basically supported. You see an example that you basically can specify an MPI operator like plus or so addition, and then you basically would have automatically the result before you go again through all the results and add up your own in a for loop or something, right? So hence it takes lots of functionality and put it all in one specific, let's say, source code line. And that is also what we will see in the second part of the course. Just to motivate just the communicators, I talked a lot about it. And there's this MPI world communicator that has all the ranks, all the MPI processes involved. But we can also create our different groups, which we will do later in the lectures. One idea is then to use these groups then for different elements. Maybe also one is for ship and one is for the waves. But this is something that we will do also in the next couple of lectures. Just take away the message that the MPI ranks and communicators have a very specific meaning, and we will talk about this also in the second part much more. So in this sense, I would break here also for the video, and we have a break here in class, but I will play the video for those that are interested. It's a nice summary